linear inequalities. And before we start to discuss, I don't know why that looks funny. Before we start to discuss them, I want you to do some thinking. Okay? So I want you to graph this quadratic I have up here. And I want you and your pod to discuss these things. When is f of x greater than 0? How would you write your answer? What sort of things are you really looking at? What are critical when you're trying to determine your answer? So graph it and just try to discuss these 3 questions up here. And then we'll move forward with how this relates to our lesson. Okay. Once you get it graphed, I want you to do some talking with your pod mates. Okay. Window range. So clear and go to zoom and hit 6. So that's standard. So now you're back. Were you like zooming in? Okay. Do you put the cover on every time? Okay.
This is the greater than 0. I think we should also.
All right, so let's talk about this. Okay? Devin, when would you describe f of x being greater than 0?
Negative infinity to negative 3 and 2 to infinity.
Negative infinity to negative 3 and 2 to infinity? And would these be parentheses or brackets?
Brackets.
I see you're saying.
Oh, okay, so it would just be.
Okay. And you changed your mind because?
Because at that point, y would be equal to 0.
Okay, so we don't have equality, so we want. Okay, parentheses. Okay. Now, he said negative infinity to negative 3 and 2 to infinity. So less than negative 3 and 2 to infinity. What on the graph is indicating that f of x is greater than 0? Why were these the intervals that he picked? Nathan, what's visually?
Those are the x-axis coordinates where the line goes through the x-axis and then they go up to infinity forever.
Okay, they go up to infinity. So since we were looking for f of x is greater than 0, you were looking at above the x-axis, right? Okay, good. And then he said something about his x-intercepts. Okay? What are our critical points? What breaks up being above the x-axis versus being below the x-axis? Our x-intercepts, right? Okay? So what we are going to do today, I am going to give you an inequality that is a polynomial to start with, okay? And we're going to need to determine the intervals in which it is true, okay? Now, yes, we could graph our polynomial and figure it out, but we also have the capabilities of finding zeros to determine where we're at the x-axis, and then it's just a matter of determining are we above or below, okay? So you won't need your calculators anymore. It was just so you could graph that without having to get crazy, okay? But I want to first talk about these polynomial inequalities, okay? We're going to do two types of inequalities. Okay, we're going to talk about polynomial, and then we're also going to talk about rational. Okay? So, when I'm asking you to solve a nonlinear inequality, I have 4 steps that I need you to take. Okay? And we've kind of talked about a couple of them. Okay? When you were looking at that graph, you saw that the x-intercepts broke our graph up into above versus below the x-axis. Okay, and when we're dealing with an inequality, I'm basically going to be asking either when are we above or when are we below 0. So the first thing I need you to find are your critical values, which are going to be your zeros. We've spent like 2 weeks finding zeros of polynomials, so I have confidence that this stuff is going to be okay. I'm then going to ask you to put these zeros on a number line. Okay? Basically, we're just going to plot them on an x-axis, but leave out the y-axis. Okay, we need to test our intervals to figure out which ones work and which ones don't. Okay? We can think about the graph, but then we could also think about which intervals satisfy our inequality. So if I plug a number in my interval and it satisfies the inequality, all of the numbers in that interval will. If I plug a number in from my interval and it doesn't work in our inequality, none of those numbers will. Okay? So we can test each interval by plugging in numbers. Okay? And then I'm going to ask that you represent your answer in 2 different ways. On a number line, I'll show you what that looks like, and then interval notation, you know. Now, I'm going to go back up to this first step. When we find zeros, what does our equation need to be set equal to? 0, so we can find the zeros. Okay, so if we have an inequality that is not compared to 0, that is the first thing that I need you to do. I need you to fix that inequality so we can compare it to 0. Okay. All right, so here is our first polynomial example. Okay, and before we start finding our critical values, I ask, and maybe, I'm going to come back, maybe you want to put like a step 0 compare to 0 so that you don't forget. That's up to you. You might be able to remember, okay? But if your inequality is not compared to 0, you need to fix that, okay? Otherwise, you can't find zeros, okay? So let's rewrite our inequality to be x cubed minus 4x squared minus x plus 4 is less than or equal to 0. Now this is the inequality we're going to work with. All right, so step one, we need to find the zeros. In order to find the zeros, I'm going to ask that you go ahead and set your equation equal to 0. Please do not worry about that inequality sign until we test our intervals, okay? I don't want you to get caught up in the inequality sign when we're trying to do the algebra, so let's go ahead and change it to an equation. Now, this is a third-degree polynomial, okay? Yes, we can use the rational zeros test and use synthetic division to find our zeros, but do we have to? Okay? If there's a different way to find zeros, that's fine. Sometimes when we have a cubic function, we can do what? We can factor by grouping. Does this look like a potential candidate for factoring by grouping? Then let's do that. Okay? All right, so GCF of the first two, GCF of the second two, and since both have x minus 4 in common, we can factor out an x minus 4, and left over is x squared minus 1. So we can factor this to x minus 4 times x minus 1 times x plus 1. All right. Okay, so here is my number line. Where did we find zeros? We found zeros at -1, +1, and 4. So this is just a number line, okay, where I plotted my x-intercepts. I'm just going to do tick marks right now, okay? These are my x-intercepts. Okay. All right, so now, since I have 3 zeros, there are 4 different chunks of our number line, okay? We have the chunk before -1, we have the chunk in between -1 and 1, the chunk between 1 and 4, and the chunk after 4, okay? And all we need to do is we need to pick one number in each interval and figure out if that interval works or not, all right? So, what is a number less than what, -1? -2 sounds like a great one. So if we plug -2 in up here, -2 cubed is -8 minus 4 times 4. Okay, so we're negative, right? So we have -8 minus 16 plus 2 plus 4. Is that number going to be positive or negative? It's going to be pretty negative, right? We have -8 minus 16 and then only plus a little bit. So we have a negative number. Is that less than or equal to 0? Yes. So this is going to work. Okay? And what we can do is we can say, all right, all of this is working. So I'm going to shade it in. And since we have equality, I can put a bracket on -1. What's a number between -1 and 1?
0.
0. Okay, if we plug 0 into our polynomial, 0, 0, 0 plus 4. Is that positive number less than or equal to 0? No. So that interval is not going to work. Okay, and it doesn't matter what the number actually is. We just really need to know if it's bigger than 0 or less than 0. Okay? What's a number between 1 and 4? 2 sounds great. Okay, so if we plug in 2, we would have 8 minus 16 minus 2 plus 4. Is that going to be negative or positive? That's going to be negative, which is less than or equal to 0. So since that does satisfy our inequality, so will the entire interval. And since we have equality, we can put brackets there. Okay, and then after 4, I would say the easiest number to plug in would be 5. Okay, after 4, we can plug in 5. We would have 125 minus 100 minus 5 plus 4. Okay, that's going to be a positive number, right? And that positive number is not less than or equal to 0, so that interval does not work. Okay, as long as you choose a number in each interval, that should give you the intervals that work and the intervals that don't. Okay, so here is your number line answer. Okay, doesn't it kind of look like interval notation? Okay, it's just on the actual number line. Okay, now if I want interval notation, it's really easy to take this and write our answer in interval notation. This interval that worked goes from negative infinity to negative 1, and then this interval goes from 1 to 4. Questions before we look at rational ones? Do you have a question as to how I chose the numbers that I plugged in? Do you have a question as to how we knew if it worked or not? Okay. Your inequality sign is what's going to tell you what to look for. So since we were less than or equal to 0, I was looking for negative numbers over here. If we were greater than or equal to 0, I was looking for positive numbers. Okay, so just keep that in mind. Okay, now, this is going to be the most straightforward way to think about whether your answer, which intervals work or not. Okay, I also could understand if you wanted to think about the graph at all to test your intervals. So if this were our graph, we have a leading coefficient that is positive with an odd degree, and each of our zeros happen once, so we know this is what our graph is going to look like. And please notice the 2 intervals that we've highlighted as our answers are the 2 intervals that are below the x-axis. Okay? So on the polynomial ones, if you wish to think about the graph, that is fine. Okay? But the testing the intervals will be a good way no matter what type of problem you're looking at. Okay. Let's talk about what happens when we have rational functions. Okay, so here I have an inequality, and here I have the graph. Okay, so first of all, I want you to talk at your table. If I were to give you this inequality, this rational function greater than 0, what would be your answer? Go ahead and have that discussion right now. Based on the graph, what would be your answer? I want to know what the answer to that inequality would be. Like based on the graph, when is that greater than 0? Okay, so what would our answer be? Sophie, how would we describe our answer? Like, where are we greater than 0?
We were talking about how the graph wouldn't go below 0, but it does.
Because it goes like right here, right?
Yeah, and the last one, like we're below 0 and the x's were greater than
Right. Well, tell me, when is this above 0? So when are we above the x-axis? Like what places? Where do you see graph above? Okay, so over here, right? Anywhere else? Or above? Okay, right here, right? Okay, so I just highlighted in blue where we are positive, right? Because I want my rational to be greater than 0. So we could describe from negative infinity to negative 5, and from 2 to infinity, we are above the x-axis, okay? Well, when we were talking about our polynomial examples, we were talking about how we need to find the zeros, and that breaks up when we're above and when we're below, okay? Well, how many x-intercepts do we have in this graph? 1. It's x equals 5, right? Negative 5, right? Well, what other x value is affecting where my graph is? What? The asymptote, specifically the vertical asymptote, okay? So not only do we have to worry about our x-intercepts, because they do affect when we're below and above the x-axis, but our vertical asymptote is also going to affect where our graph is, okay? And this asymptote at x equals 2, okay, changes where my graph is placed, right, that curve, okay, we're kind of catty-cornered from each other. So that is a critical value for us to consider. So I want you to go back to your instructions, and when it says critical values, find the zeros. You also need to say vertical asymptotes. Okay, now obviously if it's polynomial, there's not going to be a vertical asymptote, so you would ignore that one. But if it is rational, we do need to know where those vertical asymptotes are. Right? So let's go ahead and do this one. Now some of you are getting really excited because you're ready to find the zeros and the vertical asymptote. However, what is the problem? Oh, we're not compared to 0. That is the first thing you have to do. If you don't have that inequality sign with a 0, then you better fix it. Okay? So, in this case, we need to subtract that 3 over. Yes.
On the problem for the bottom side, it was
It was. Okay, now do we have just one, like, is that something that you've graphed before? Like, is that something that we graphed over the weekend? Okay, we've never seen, like, a fraction in -3, have we? Okay, if we want to identify the zeros and the vertical asymptotes, we need just one big fraction. Well, right now we have a fraction minus 3. So in order to force this to just to be one fraction, what are we going to need to do? How do we take that minus 3?
Multiply by the reciprocal of x plus 5 on both sides to get it to not be a fraction.
Well, if we multiply x minus 5 by x plus
Then
5,
0 will be 0.
well, it wouldn't get rid of our denominator because x minus 5 times x plus 5 is still going to be polynomial. That works with imaginary, is what you were thinking, and that would be a great strategy for an imaginary number, okay? But when we have a fraction and we're adding and subtracting another value, what has to be true in order to actually perform that addition or subtraction? We have to have the same denominator. Okay, so we need to force this guy to have the same denominator as this first fraction so that we can actually combine them. So if this denominator is x minus 5, then this denominator also needs to be x minus 5. Okay, so what happens is now we have a common denominator of x minus 5. And we have 2x minus 7 minus 3x plus 15 in our numerator because we can combine everything together. That negative 3 does get distributed to the x minus 5, which is why I have the plus 15. Okay, and now what is my inequality? X minus 5 is still my common denominator, but what's in our numerator?
Negative x plus 8.
Negative x plus 8. Okay, so this is what we need to be working with in order to determine our intervals. Okay. On our number line, we need two things now. We need our zeros and we need our vertical asymptotes. We're really good at vertical asymptotes. Where does this rational function have a vertical asymptote? At x equals 5. Okay? And I'm going to make a note to myself that that is a vertical asymptote because it makes a difference if it's a vertical asymptote versus a 0. Okay? We got our vertical asymptote by setting our denominator equal to 0. Now we need a 0. How do we determine our 0? Okay, we got to set it equal to 0 and solve. And when you set a fraction equal to 0, what are we really looking at? What's 0? The numerator or the denominator? Okay, if we set our fraction equal to 0, we got to multiply that denominator over. Well, anything times 0 is 0. So when you're finding x-intercepts, it really only matters where your numerator is 0. And where does that occur? At 8. Okay, so your numerator set equal to 0 is your 0. And your denominator set equal to 0 is your vertical asymptote. Okay? Now let's go ahead and test our intervals. Okay, please choose numbers that are nice to plug in. Okay? You're doing some mental math. All right? And really all we care about, we want these numbers to be negative or positive. We want them to be negative because we are less than or equal to 0. So what is a number less than 5 that we can choose? 4, 1, 0. It doesn't matter. Does it matter? No. Okay. I'm going to choose, well, I heard 4 first. So if we take negative 4 plus 8, that's positive, right? And if we take 4 minus 5, that's negative. So our fraction becomes negative. That works, right? Okay. And so all of this is going to work. Okay? I'm going to wait for a moment on my parentheses and brackets. Okay? Between 5 and 8. 6 sounds like a great number. Negative 6 plus 8 is positive. 6 minus 5 is also positive. So we have a positive numerator, a positive denominator, makes a positive fraction. That's not what we want. Okay? And then above 8, okay? Like I said, it doesn't matter, just make sure it's easy to plug in. Okay? Negative 9 plus 8 would create a negative numerator. 9 minus 5 would create a positive denominator. So negative divided by a positive would make our whole fraction become negative, which is what we want. Now, I held off on our parentheses and brackets because we need to talk about something. Okay? We have equality here, right? Okay. At 8, this is our 0. Do we have a coordinate on the x-axis? We do, which means we can include it. Okay. However, at x equals 5, we have a vertical asymptote. Do we have even a coordinate at x equals 5? No, we cannot include the vertical asymptote because there is no coordinate there, and there never will be. Which is why I labeled 5 as a vertical asymptote so that I would remember, hey, don't include it in your answer. Okay? Now, if we didn't have that equality bar, it wouldn't matter. Both of them would need parentheses. But where we have to be careful is when there is that equality bar, and we have to determine which ones do we include and which ones do we not. Okay? So our interval notation would be negative infinity to 5 and 8 to infinity, making sure we put brackets and parentheses around the respective 0 versus vertical asymptote. All right, what do you think? Okay. We've been pretty quiet this morning. It's Monday. I get it. Okay, so what I want you to do, have one person open up a book or take a picture of the book or whatever. I want you to try one problem before you leave. Okay? So we have about 8 minutes left in class. You might get to do 2 problems, but by the time you get set up, maybe just 1. But I want you to try one problem before you leave. And if you have a question, you got to ask me about it. Okay?